All right, community. How are you all doing? Happy to be here. Thank you for sticking with us. Next up, we got Our Journey to Achieve Event-Enabled Autonomy by Breed Digital. They're an autonomous delivery startup based in the Netherlands. They are on a mission to create hassle-free last-mile delivery using drones. Our speaker, Ram Gandhi, is the co-founder and fellow developer at Breed Digital. He's calling in today from the Netherlands. Deepak Singh is a final year undergraduate student majoring in electronics and communication engineering from NSIT College Delhi, currently working as a technical research intern at Breed Digital. On this talk, they will share their learnings and the realization of a forward-looking autonomous drone delivery architecture. Community, please welcome Breed Digital. Mike's all yours, guys.
Hey, welcome everyone. Hello, my name is Ram.
Hey, I'm Deepak.
Let me share my screen a moment. Okay. We hope that you're having a bright day like the slide is going to have. And thank you for your interest for attending this event. And it's really a great pleasure to be speaking at this event. And thank you very much, Cone Foundation as well. We have a lot of interesting slides coming up, and we hope to make you stick till the end. It's a great slides and great presentations all around last few days, and we're very impressed with it. And that's why we have something else very interesting as well. I trust we will keep you stay until the end of it. This is what we're going to talk today. How do you enable event-enabled autonomy for your drones? That's us, just in case. We are Breed Digital. We are a very early stage autonomous delivery startup based in the Netherlands. Our mission is to create using drones. And as you see that we are spread across the globe, and who doesn't like open source? Come on. So we design, build, and also code our drones and the ecosystem around it. And we truly believe that the higher levels of automation across the chain is going to make the drone delivery very affordable. And to just make this happen at Breed Digital, we have a code name project just for this thing to happen. We want to enable restaurants to deliver flying food. And as you can already imagine, there are so many moving parts involved in delivering stuff with drones. And you got to keep so many systems in hotline. And there is a great deal of autonomy that's needed at every stage in the architecture and your solution. Reality. So what we want at the end of it is really take your hands off and let the system do the magic. So autonomy in and out was very, very important for our dream to make it happen. So why event-enabled autonomy is so important for us, and what the role it's going to play to enable the forward-looking drone delivery architecture. So there are a couple of aspects that we felt in when we started up, and there are some of the things I'm going to list down here. The very first one was the over-the-air updates. So we want to make sure the source code that we change, the code that we do for the drone is really landing on the drone, irrespective of whether the drone is offline or online, because everything is cloud connected these days. And you also want to make sure that's very reliable, secure, blah, blah, blah. At the same time, there are so many moving parts involved in this solution, and we want to make sure the transmission is always reliable over unreliable connections that we all have across 3G, 4G, 5G, whatever. And what's also very important is this thing, which most of us are aware of, is it works on my machine syndrome. We want to really avoid that from the ground up. We want to make sure whatever piece of software that we build is truly reliable enough that it runs on the real hardware. And we want to get the testing confidence while we are building our solution from ground up. So what we have for that is simulation on steroids. So I'm going to take you through a slide on that, on how we perceive simulation in our software development lifecycle and how it's really helping us to up the game. And the last or the lead, what I truly believe is that developers are happy when they see their code in action. So it's really our responsibility to make sure the piece of code that's written and the moment it's deployed onto the drones, real or virtual, the end-to-end time should be really short, because the moment you have given that acceleration to these features to reach the target state, the more energy the developers would get. So hopefully they will consume less coffee, who knows? So we believe that the key to the designing such a forward-looking solution is lying in the embracement of your events that are happening across the in or out. Let's dive right in. What is event-enabled autonomy? That's the topic of the day. So what I did was I looked up on the internet to see if I could find a definition that I could use here. But there is nothing like an event-enabled autonomy that's termed or coined so far. And Google Trends across all the history shows me that. So maybe it's time for us to define it. Why not? So let's take a moment to define it, so we are all on the same page. So event-enabled autonomy is as simple as achieving autonomy by sourcing events. So by what I mean is, in a plain English, events are nothing but an action or an occurrence that happens. For example, a low battery event, or a mission is in progress event, or a no-fly advisory event. And these kind of events keep happening all around us, either on board, off board, all over. And autonomy is really the capacity to take or make informed decision. And it could be obstacle avoidance, or it could be also emergency landing, and many things like that. So imagine if you could source all these events, off board, on board, cloud, whatnot, and the system of interest, and it can do the magic, necessary actions. That's exactly what we would like to term as event-enabled autonomy. So I have a very small example. So let's see it in action. So at a very, very simplistic level, again, as I said, it's a very simplistic level. This is how an event-enabled autonomy would look like. So you see that the events from the drone are coming all the way into the PubSub bridge, which is in the middle. At the same time, there are events that are originating from the cloud that's on the right side. And there are various types of events. It could be like from the drone, for example, you could have a pre-flight check event, successful or failure or whatever. Or it could be also mission progress event, or a health probe event, telemetry event. So what's interesting here is sourcing these events from all around and creating some sort of a hub wherein interested parties can actually tune into this particular to make sure that they react on time. And by doing this approach, what we have achieved is we created a decoupled architecture across all our modules. And by decoupled, what I mean is we got greater flexibility to kind of compose them and create complex workflows without having to worry about making changes to the core components every time that we want to make things different. So how do you create such a system? We have been spending some time on it, and enabling this event-driven approach has been very important for us. So we have made 3 design choices. When we sit back and think through, these are the 3 prominent ones that popped up in our head that we would like to share with you. And hopefully you can make your own impression of mind maps of how you see things in your perspective. The very first one is very interesting. It's a C++ and or Python in our context. So share his findings on this topic. Over to you, Deepak.
Oh, hello, everyone. Thanks a lot, Ram. Hello, everyone. So here we have a demo showing the obstacle detection algorithm in running. So on the left, we have the algorithm written in the code written in C++, and on the right, we have the code written in Python. So when it comes to C++ versus Python, C++ has a very clear edge in FPS or in the memory footprint. With C++, we were able to achieve 22 frames per second, whereas with Python, it was only 14 frames per second. And when it comes to memory, as can be seen from the graph, C++ had a lower memory footprint. So in this case, C++ is the clear winner. Let's have a look at the other aspect of things.
Okay, I think Deepak is having some troubles, probably. So when you look at it from a build perspective, what you do with C++ is you actually build the native machine code suitable for the underlying operating system and also the processor instruction set. However, for Python, you actually build the bytecode, which is consumed by the Python interpreter. So with that specific aspect has been a great importance for us because you actually build once and you can deploy the code Python anywhere. And it is very important, and you will realize it in the next slide by saying it. So in this slide, I assume all of you agree that Python is a winner when it comes to build once and deploy anywhere. So it's a tie, basically. So we want to take you through the reasons why we chose Python over C++ for us. It was really a very hard decision for us to kind of switch in the middle of our, assignment or mission, that we move all the way from C++ to Python, because naturally we started with C++ for all the low-level programming, and we chose Python for doing the high-level stuff. It could be integration, orchestrations, and stuff like that. However, we realized that in order to write a reliable software, you need to have a parity between simulation and production situations, environments. And how can you bring the parity is by making sure that you build and you test the same piece of code and same binaries that is deployed on the drone at the end of the day. And in order to reduce or bring in the parity between these two environments, we realized that building native machine code on the real hardware was very challenging when we use C++, given that we cannot have we can have a ceiling when it comes to automation at scale. So there is some level of ceiling that we felt. And with Python, when we moved in, we write once, we push it to a drone without any exclusive compilation steps. And second one was Python being a high-level language. It was very faster to develop, and we see the progress that we are making day in, day out. And also the ever-growing third-party libraries. So the Mavis Python is a very classic example of it. It's a prime example, and it really enabled us to tap into the PX4 ecosystem via the Python bindings. And it's a very big thanks to all the contributors of the Mavis Python, because for let us focus on our position without having to worry too much about the PX4 internals. And the last is really the developer well-being, which I keep coming back because it's very important for us to reduce the time to deploy our changes all the way across the ecosystem that we have. And Python really helped us in that line. Second one is, when would you use edge compute over cloud? And this is also a very classic question that we all get, is it suitable for edge or it's suitable for cloud? So I tried to list down some of it from our experience in this slide. We see the need to use the power of the edge when it comes down to these three things, or even more. The first one is physical connectivity. So if you see the need for sense and respond, sense avoid, or even local connected devices that you want to leverage, then there's absolutely no other choice other than doing this stuff on the edge. Number two is time sensitive. If you have latency sensitive activities like obstacle detection avoidance or even acts of emergency, that's exactly when you would also choose to do things on the edge completely. And the last is privacy sensitive. So you might want to, for a situation like in Europe, for example, we have a GDPR and all privacy regulations, making sure that the vision data and the location data of the things we see and we watch has to be handled very carefully. So probably that's also a reason why we could do things on the edge itself. There are many more other things, like if you want to save some power, you want to avoid a round trip to the internet, probably you want to do it offline. So there are so many aspects like that. You could use edge over cloud. So Deepak has a very interesting example to show it over to you. Over to you, Deepak.
Hey,
Are you
thanks, Ram.
back?
Yeah.
Yeah.
So hello everyone. Here is a short demo of our obstacle avoidance algorithm. So we use the PX4 SITL and the gazebo simulator for simulating the same. On the left, you can see the gazebo world, and on the right, we have the Q ground control, where, as can be seen, we've planned a mission using the GPS coordinates. Now, the drone is equipped with an RGBD sensor, simulating closely to the hardware that we have, and the drone has to reach that goal location while avoiding these obstacles. So let's see the drone in action. As you can see, it's taking off. Now, using the RGBD sensor, drone creates a local depth map using which it computes trajectories and the control signals. As you can see, it took a turn around the tree, and now there's another obstacle coming in front, and it will plan a trajectory around this. For doing this, we use the offboard control mode in the PX4 firmware. Yeah. So what happens is when it encounters an obstacle, it changes mode from mission to offboard. And when there's no obstacle in front, it changes back to mission mode so that it can execute the pre-planned mission safely. So it has reached this waypoint. So yeah, so this is the entire stack. As you can see, we have an RGBD sensor, which basically passes the point cloud to the companion computer, which is running the detect and avoid logic. So it initially checks for obstacles. If there are no obstacles, then it continues the mission. If there's an obstacle, then it changes to offboard mode. It gets the current drone state using the Mav SDK Python API, and it generates the velocity command, which is passed to the Pixhawk using, again, the Mav SDK Python API. Over to you, Ram.
Thank you, Deepak. It's very important to mention to everyone that the moment we chose to switch to Python, and it really helped us greatly, because then we could focus more to compensate the underperformance of Python in its raw form with using NumPy and other libraries. Along with that, we leveraged the asynchronous libraries of Python to make sure that we utilize the OS threading very effectively on the edge to make sure whatever you see on the slide happen at a very low cost and no footprint on the CPU. The next up is really when to cloud over edge. And that's really the last topic that I have today. So there's several advantages of choosing cloud over anything. And primarily it's because it's 24/7 available, it's scalable, and it's secure, and so many things. Still, we do see there are very exclusive requirements when to use cloud over the edge. And those are, the first one is reliable transmission over unreliable connectivity. So we know that things are not always connected and there's always a blip in between. So we solve the problem using a very classic pub/sub pattern in a store forward mechanism based on the type of the data between the drones and the cloud. And as you can see, the autonomy is in both sides. Even the cloud is autonomous in its own aspect, and the drones are also autonomous in their own cocoon. And we make these two autonomies talk to each other with the help of event streaming across both the sides. And we got to make sure that we design the solution for failure, and which essentially means the command data, the result data, or the over-the-air updates that go in back and forth, all of that, we should not lose it at any given time. So this approach has been, even if the drone has been shut off for say 30 minutes or 1 hour, our over-the-air update has been always waiting for the drone. Whenever it comes back up online, the entire solution software has been overridden on the drone, so it's ready to fly off in the next mission. So the ability for us to push our code updates back to the drone in less than a few seconds is really what is enabling us to move fast. And this loosely coupled design from the ground up is also another important thing to observe. is the way that we can do hand-on and hand-off between these components is very interesting. If we kind of split them up using pub/sub mechanism, it enabled us to create complex workflows without having to deal with individual modules. And the last one I have is a simulation. So how do we do simulation in the complicated world that we have today? So this is a workflow. I can show you on the left side, these the world. So they do the thing. And when they create a feature, then it's basically going to be get shipped over the air onto the virtual drones that we have created on the cloud and also the real drones. So what it happens is that inside the cloud, we have provisioned very high GPU virtual machines, which exactly contains the drone stack, the mock sensors, mock actuators, and we have camera streams and the drone dynamics as well on the cloud. So this really let us make sure we create a synonymous environment, very similar to the production situation, right on the cloud, right in the simulation situation. So the dev, just a matter of few seconds, should be able to connect over virtual GL, over VNC to it, and they can actually see the encoded, decode 3D graphics from Gazebo or RViz and stuff. So it really enabled the acceleration at which we can move forward. And it only takes a second to fire up virtual machine on the cloud. So with this approach, what you see, the tooling on the right side is what we use for simulation. We believe that it will enable the developers to push source codes very faster, and the features additions will take them much farther. And we get the testing confidence as well as we move forward. So with that, really completes our talk, and we hope you enjoyed it as much as we do. And last but not the least is, yes, we are hiring. So we are really looking for go-getters, and we promise there is never a day without coding. So come talk to us. Thank you for listening. Over
Awesome.
to you, Ramon.
Thank you. Thank you, guys. Great presentation. So we regrettably ran out of time, but Breed Digital is going to be on Slack. Please join them on Slack if you have any questions. Feel free to ping Deepak or Ram directly there. They're both of them there. Thank you guys again.